Is this working? Hopefully. It does work. That's good. Okay, so yeah, it's 6, so I guess we're gonna get started. Today we're gonna be talking about console hacking, specifically the Nintendo Switch. We're going to be leaning somewhat on last week's talk where we learned about embedded systems, threat models, and secure boot chains. There's a lot of really important foundational information there, so if you didn't see it and don't know what some of these words mean, then maybe check that out before coming back and watching this again. So my disclaimer here is that I was involved a lot with the 3DS scene, and a lot of the same people carried over, but my involvement with the Switch scene was somewhat limited because I started school around that time and didn't have a lot of free time. So none of this is my work, but it is very cool, and I know a lot of these people, and they're awesome. So there's too many people to credit, but there's a few groups: Reswitched, SwitchBrew, FailOverflow, and then there's a lot of awesome people. Mike, Moat, they did really awesome work on a lot of the low-level bootloader stuff that we'll see coming up. And then Geek at Work from Esper and Q3K from Dragon Sector, both CTF teams that some of you may recognize, gave a pretty cool and accessible talk at a CCC-affiliated conference event that is also really good and goes over a lot of the public information around this, so you could also watch that. But yeah, we're going to get started. So the Nintendo Switch, I'm sure everyone knows what it is. We will be talking about the original Switch, not the Switch Lite. The Switch Lite has a new hardware and is very different. So the hardware of the original Switch is an NVIDIA Tegra X1 system on a chip, and it contains a Maxwell GPU, 4 gigs of RAM. It's a pretty powerful machine for mobile console, one of the most powerful we've seen ever, basically. The X1 is also known as the T210, which is a internal codename the developer codename for the chip. It has a lot of public resources available. There's a 3,000-ish page developer reference manual that you can just download. You don't need to give them an NDA or anything, and it has a lot of good information. It does not document a lot of the security measures, unfortunately, but what can you expect? You can also buy the dev board. I think it costs like $700, or used to cost $700. Don't know what it is now, but you can also get a student discount. It's pretty good. There's a picture of it on the right. So as far as the software goes, there's a customized NVIDIA closed source bootloader that is completely proprietary. The OS is also completely proprietary. It runs Nintendo's custom microkernel based thing they call Horizon. It has a lot of modern security mitigations like NX, ASLR, KSLR, privilege separation boundaries between kernel and user land, and et cetera, et cetera. And then the GPU we talked about is actually basically the NVIDIA Linux GPU driver with like a fancy wrapper thingy that translates all the calls, which is pretty weird and interesting. So the first thing we're going to be talking about, since this is about embedded security and a continuation of our embedded security talk from last time, is threat modeling. So when we recall that a threat model is an abstract model of attack vectors and countermeasures, where we're considering what kind of security makes sense for a target. In the case of a switch, we want to be asking and answering all of these questions, like how critical is it? What is the attack surface? What do attackers have to gain? And how do we constrain the operation of the device? So the Switch is, as a game console, a very high-risk system in terms of financial impact. It has the manufacturer, in this case Nintendo/NVIDIA, is highly incentivized to prevent any unauthorized code from executing on the machine and imposing DRM to the best of their ability, because they are very concerned about piracy, of course, and a couple other things like quality control, but mostly piracy. There's a high chance of hardware attacks because in this case you are trying to defend the system from the user of the system, which is a very difficult, if not impossible, challenge, but we will talk about that a little bit. And the device is also internet facing, so there's a lot of attack surface all over it. You're trying to basically protect it from not only outside attackers that might try and come in with like wormable exploits over the internet, but also you're trying to protect against the user themselves, who might be inclined to take the device apart and start soldering things to it and trying to figure out how it works and dump some keys. And as we discussed, there is a lot of potential revenue they will see it as hanging in the balance of the security. So the threat model is, unfortunately, for the manufacturer, very difficult to secure against. So with that in mind, we're going to be talking about the secure boot chain. So remember that we have microcontrollers, which will begin by executing a boot ROM. And your boot ROM is some executable code that's masked in at the factory. It's read-only and can't be updated, and it's your first phase of the boot chain. And as we boot the system, we're going to be increasing in complexity by loading more and more stages that initialize more and more of the hardware. And if we want a secure boot chain, each stage of the chain is going to need to be verifying the next link in the chain to ensure that it's a both authenticated link, in that it has an origin that we know and comes from either a manufacturer or an authorized third party. And also we're going to want to validate that the chain has integrity and that it hasn't been corrupted. And so the chain needs to have a beginning, and the beginning is going to be our root of trust. In almost all cases, this is the boot ROM of, if not the primary processor, the boot ROM of some processor in multiprocessor systems. So we might already know from the last talk that multi-stage bootloaders increase in complexity, and that was one of the reasons we gave for why a boot chain is necessary, because you need to initialize more and more of the hardware. But we also want to consider that multi-stage bootloaders have another function, which is to decrease privilege levels. So at every single step of the chain, we want to be basically removing privileges as we jump into the next link, so that the next link is more confined and we're only ever dropping capabilities, so the fundamental constraint of the system imposed by the boot ROM stays constrained, or stays enforcing that constraint. And on ARM, we consider these execution levels. So there's Trust Zone's secure monitor, and that runs at execution level 3, and this is the highest privilege level on an ARM core. Then there's a hypervisor level that is usually not used. It is very occasionally, but not really. And then the kernel runs at execution level 1, and then your user space applications run at execution level 0. And also, on a lot of embedded devices, you might have a security coprocessor that has more privileges than your normal processor. On the 3DS, for example, you had two processors, just one application processor and one security coprocessor. And the application processor wasn't directly connected to any of the critical hardware, so you actually had to ask the security coprocessor to do a lot of things for you. Like if you wanted to read from the flash chips, you couldn't decrypt them, so you needed to ask the security coprocessor to use the AES engine to decrypt the flash for you. And in that sort of idea, we actually have more than just one secure boot chain. Each processor might have its own secure boot chain, and one of those processors might be the real root of trust that initializes the other one, usually your security coprocessor. So your boot ROM is, as we'll recall, the highest level of privilege almost always, other than in the case where there's a second processor with higher privileges that does more of the initialization, as we just discussed. And the boot ROM will, as I want to really stress, impose the fundamental constraint of the system, because embedded devices are usually replacing some kind of dedicated circuit, right? We want to generally make sure that your embedded device is only performing the task that we intended it to and not executing whatever arbitrary code, or at least as a manufacturer, that is what you want. As a user, that is maybe not what you want, but that is something we can discuss. The boot ROM is also the holy grail for bugs because it is unpatchable. It does its best to stomp on our homebrew, as we can see on the right with our boot ROM, but if you can find a bug in it that is a full compromise of the root of trust and is an unpatchable full compromise of the root of trust. So, yeah. On the Tegra X1, you have the root of trust is actually a separate processor from the main application processor. It is called the Boot and Power Management Processor, the BPMP. It has this thing called the iROM. This is basically just the boot ROM that we have discussed before. And it has Nintendo's public key in it, and it will use that to verify the next stages of the bootloader. And the public key is stored via fuses. They're not real fuses, but in an embedded context, a fuse is basically a region of memory that can be written to once ever, and usually this is at the factory, and then you can normally not rewrite these regions. There's a separate thing that you basically use to seal them. So the public key is written in at the factory, and you can't ever change it. So theoretically, the iROM running on the Boot and Power Management Processor is going to be imposing the constraint that only Nintendo's public key will be allowed to run, and you'll only ever be able to run a kernel that Nintendo has signed. And then there is the application processor that they call the CPU complex, or CCplex. I'm just going to call it the application processor. There's multiple cores, but it's conceptually an application processor. So the developer documentation is light on security details, as we discussed for the boot ROM. But when we're thinking about attack surface and we want to be looking for bugs in this secure boot chain, one thing immediately jumps out at you, which is the Tegra RCM, which means recovery mode. So it runs this applet that they call NVT-boot-recovery, which basically means it is a separate binary, but it's still in the iROM, so it's also read-only. It's mostly a semantic distinction, but so the NVT boot recovery is like a special mode that the processor will boot into if it encounters a failure of some kind, or maybe if you hold certain buttons or whatever. And then normally during a normal boot execution, it'll jump into NVT boot. And so what is RCM? What is this recovery mode? Well, it's a USB recovery mode. So it is used primarily for provisioning devices. It is enabled on production devices. And the idea is that if you somehow manage to completely break your system in a way that normally wouldn't be recoverable, well, Nintendo in this case, or manufacturer in general, because it's a system-on-a-chip platform that's used on a lot of different devices, the manufacturer is going to want to be able to recover devices that have been damaged, or the software doesn't work anymore, and instead of it just becoming a brick. So this sounds like a really awesome attack surface as someone who, if you're the kind of person who wants to run your own code, but unfortunately the commands need to be signed with the key that is in the iROM. So it's either RSA or I think AES CMAC or something like that. Basically, if you are not Nintendo, you can't issue the commands to do things like run new executable code to provision the devices. Okay. Yeah. So even with the commands being signed, and this limits a lot of the functionality that we can interact with, but we still get to interface with the boot ROM in some way, because you have the whole USB stack essentially, which is a notoriously complex like networking based sort of stack where you have like different nodes and endpoints, and there's all this complexity and stuff going on, and it's essentially this huge attack surface that interfaces with unknown devices, and it's unpatchable, which might seem like a bad idea if you're a manufacturer, but I guess you have to consider the trade-offs of having the devices be either fully secure and completely unrecoverable, or be actually repairable in the case that the software is corrupted. So maybe we can still find a bug. But first, we need to get the boot ROM. Because if you think about it, how do we even look for bugs in a USB stack that we can't read, right? We don't have the code for the boot ROM, it's just in the chip. So we need to get the boot ROM to reverse engineer the boot ROM, which is easier said than done. As I said, it was these boot ROMs are usually mask ROMs that are masked in at the factory, which is like a term for referring to photolithography. But all you need to know is that it essentially gets like kind of burned in for our intents. So here's an image that I had in the last presentation, which is the picture of an MSP430 boot ROM by Travis Goodspeed. And as we can see, it is like a circuit that is optically visible with the gates comprising the code just right there. But this is on it. So to get this picture, right, you're going to have to essentially take off the packaging around the CPU die that you want to be examining. And then you're going to need to use a microscope to find where the ROM is stored and actually convert this to code, which is possible, but is going to be extremely time consuming. So here is the Tegra X1 development board, which they also call the Jetson TX1. And it runs the same boot ROM as the switch, and it runs Linux via U-boot, which is a very common embedded bootloader, which lets us, as a developer, run whatever code we want. And it actually lets us customize the NVT bootloader, and we can sign it with our own keys. And or in the case of running in non-secure mode, we could just run it. And this lets us essentially run new code that we wrote right after the boot ROM finishes executing. This is very, very useful. It doesn't give us the boot ROM, but it means we don't have to exploit the switch and get all the way to code execution at that point in time. It just saves a lot of hassle. And since it's the same boot ROM fundamentally because it's based on the same platform, getting this boot ROM is theoretically the same as getting the switch boot ROM. So we can't read it out via software. Unfortunately, it's not that easy. So there is this thing called the Secure Boot Control Status Register. Basically, this is a register that controls a lot of things about the secure boot process, and you can read and write to this register if you have permission and you're running in the right context. And it has this field in this register called Protected IROM Disable, and basically the boot ROM sets this field on the register right before it jumps to our code, the NVT boot, which it loaded off of the flash. So it's going to set this bit, and when this bit is set, it basically means that when you try and read the region of the boot ROM, you're just going to get back this pattern, FE, FF, FF, EA, just over and over and over again, instead of the actual thing that's there. If you know any ARM, you might see a lot of E's here and go, that's a kind of weird thing for it to be returning. Why not all F's? Well, this is actually a branch 0 instruction. I'm not honestly sure why. I guess is to ensure you don't accidentally run the boot ROM twice after it's been locked or something. It'll just jump to 0, which I believe is not actually mapped. So that won't, I don't know why they did that. You actually kind of see this a lot in embedded devices, as like secure embedded devices, where it tries to store secret keys and like other kinds of data they don't want you seeing inside the boot ROM, and then it'll disable reading of that boot ROM right before like going to any modifiable code, so that in the case that that code is has a vulnerability in it that has been exploited, you can't actually read back out those secrets. So yeah, we have these two options. As I said, you can decap the chip and get the kind of picture that we saw earlier of the MSP430 boot ROM, where you expose the die and you visually recover the code that's being run. But it's very time consuming, very expensive. Well, relatively expensive. It depends on what kind of resources you have at your disposal. If you already have a lab or can rent time at a lab and have the expertise, it's not that bad, but it's still very time consuming. You have to visually convert these gates to code, and on a modern SoC they're very complex and it'd be a massive pain in the ass basically. And you also can do this thing which we actually did, and basically everyone actually did, which is a glitching attack. So if you consider the idea that there is essentially on this secure boot control status register, there's a single bit which says whether or not the IROM is disabled, and it just has to be a 1 or a 0 essentially on this single bit that controls whether or not we can read out all of these secrets, all of this protected data. And when the CPU does a write to this region, if it's just writing 1 bit and then later it'll be checking that 1 bit when you try and do the read, that is a very bad idea basically in this kind of context. Disclaimer, I am not a hardware person, but I will try my best to explain this. So your idea is that when you do this write to this register, you're actually going to be traveling a few buses to get to the CSR registers, and you're basically in a glitching attack trying to induce any kind of fault which prevents this register write from actually occurring. So if the value that gets written to the register, because you don't write a single bit, right? You write a whole value on the bus. So if it writes the wrong value that does not have this bit set, if it just doesn't write because you drop the voltage and getting into hardware stuff, if the voltage is too low, right, you won't accumulate enough charge and you won't actually flip the bit. If the clock cycle is late or too early, then the write won't actually go through. There's all these other different types of faults that you can induce, and there's no glitching protection on this. So in more secure platforms, you will have glitching protection, which is essentially the software will do more complex things to check whether or not a state is true. So if the state is that the boot ROM should be locked, instead of having a single bit that you're just checking to see if it's a 1, then we're good, and if it's a 0, well then we're gonna do whatever. Instead you'll have large whole words that need to be set to any value basically in order to disable the boot ROM, right? So if it's a 0, it's unlocked, and if it's a 1, or if it's any value that is not 0 up to 8 bits or 16 bits or whatever you wanted, then you would be locking the boot ROM. And this means that even if you glitch the check or the write and it writes the wrong value, well, it still wrote a value that is not 0. So the glitch didn't actually work, and you don't get to recover the failed information. And there's other glitching protections that you can employ, like you can have a loop that'll write to a value and then read it and make sure it's the same one that you wrote, and do that a few times, and just generally make sure that the write is working and that nothing is externally interfering. Because in the presence of glitching as a threat that you're considering in your threat model, your code actually becomes a lot more complicated, and you need to consider even though your code may have no bugs in it, things might still go wrong. So this is really interesting, but I am not a hardware person, so I won't be able to give you a super detailed explanation. The talk at the beginning that I mentioned, the 34C3 affiliated talk by Geek at Work and Q3K, is really good in going into the detail of why this works. So you should definitely watch that. But when we're trying to perform a glitch on this sort of situation, we have some difficulties. So one of the difficulties is that we need to time our fault that we're injecting to the exact right time. So we want to glitch a single instruction. We want a single write to fail, but we can't crash because we need the boot ROM to stay unlocked, but it still needs to jump to the our code that executes afterwards so that we can read out the memory and write the boot ROM somewhere else and recover it. So how do you do that? Well, the way basically everyone did it is that they used the eMMC as a timing reference. So the boot ROM has to load your code, and what it does is it loads the code into RAM out of the flash, and then it will validate it. It'll make sure that it's the signatures pass or whatever, and it will disable reading of itself, and then it will jump to your code. So the most stable external timing vector that you can rely on is that the read from the flash is going to directly almost precede the actual instruction that writes this register. So the idea behind glitching is basically this is a very brute force approach. You're going to wait for the eMMC to be read, and then you're going to wait some arbitrary amount of time. It's just time. And then you're going to do your glitch. And most people, I think, used a voltage glitching attack. So you just ground the whatever voltage rail the CPU is using. And so you do this for a very brief amount of time so that whatever instruction was trying to execute doesn't, basically. And then you stop that so that the system doesn't just break and explode. And then you check if it worked. So your code will basically, your NVT boot, custom code that gets loaded off the flash, hopefully it's still running and your glitch didn't break that. But assuming it's still running, it can check, is this register set? Is the boot ROM unlocked? And if it worked, great, you have the boot ROM. If it doesn't, you need to adjust that arbitrary amount of time that you're waiting. And this is a time measured in nanoseconds. You usually will be using an FPGA for this, field programmable gate array, which is essentially a programmable circuit that lets you do these kinds of things. But yeah, so this is from a different talk that was at 34C3, and I'm not even going to try and say this name because I will butcher it, but this is one of the switch brew people who also glitched the switch. And they didn't actually do the glitching attack on the development board. That's a real switch main board on the right, hooked up to their FPGA, and they glitched to do the exact same thing that way, but still very cool. I think I know at least 3 or 4 different groups did this kind of attack, but it's really awesome stuff. And eventually this works. So the write to the secure boot control status register fails, and then you can just dump the boot ROM out over UART, because if you're on the development board, you can dump it out over UART. I don't know if the switch has UART enabled or not. And now you have the code. You can look for bugs, which it's amazing how much work it actually takes to get to this point, but such is life. So we have the recovery mode that we know is this huge attack surface, and we want to look for bugs. So USB, how does USB work? A lot of people might not know much about USB, even though it's this really, really common protocol that does a lot of stuff in your machine. And basically USB is a network type of system. It's honestly incredibly complicated. It's a tragedy that this is still what we're using in the modern era, but it kind of just has evolved over time. And I believe Intel is responsible for a lot of this, but you have essentially this entire network architecture type of thing where you can have multiple different endpoints that all communicate with each other, and you can send these packets around that can get routed between different components in the USB stack on the other end. But the two main things we need to know about are the control the control endpoint and the bulk endpoint. There's other endpoints like interrupt and asynchronous, but the control endpoint is basically the one that will always be there. It has functions you can, or you can send certain types of packets that basically call functions on the other end. So you can query like the device status on the other end, or you can say I'm ready for setup or whatever. The bulk endpoint is I'm going to send you a bunch of data, and it has no guarantees about how fast that data will get there or what the latencies will be. It's just I have some data, I want to send it. So if you're going to use USB to copy a file over like off of like a flash drive or something, right, you will probably be using the bulk endpoint, and your machine will request like the data, but it doesn't really matter when the data gets there. It just needs to happen. And then there's interrupt endpoint, and these endpoints, other than the control endpoint, there can be multiple of them, and they're independent of each other. There will always be one control endpoint, just so that you're a valid USB device, but you can have like 2 bulk endpoints and 1 interrupt and 0. It doesn't really matter. It's up to the manufacturer of the device. But generally speaking, these are the common ones you'll see. And interrupt is basically you have a small, very bursty data transfer that's has guarantees about latency. And asynchronous, you're going to be having a continuous stream of data. So if you have a microphone plugged in over USB, you don't want to use the bulk endpoint for transferring that data because you have no guarantees about how long it will take that audio data to get there. And that's very bad because you might have like timing windows that get missed and like the audio's dropped and like all these sorts of problems. So this is the endpoint that solves that. And yeah, so they can all be used simultaneously. You can send like packets to different endpoints doing different things and receive replies in arbitrary orders. It's very much like a network, and you can use them all completely independently of each other. So in the case of RCM mode, we're going to have control messages, which are standard USB control endpoint messages that you can query status and blah, blah, blah. And then RCM messages are exchanged over the bulk endpoint. And all of these messages are supposed to be authenticated, and they can contain an optional payload that needs to be signed. Like you might have, say, an RCM message that says, I want to load some chunk of code, and then your payload might be that code. And then the code needs to be signed, of course, for security. But this is useful for recovering a device because you might have the device completely, just the software is destroyed, you can't use the device at all, and you need to bootstrap something more complicated into memory that will run at this privilege level. So you might have like a recovery applet that you're going to be loading over RCM mode that gets executed. And this payload can be fairly large, so that's why it's sent over the bulk endpoint. This is what the memory looks like. You have your RCM message in RAM at the beginning there, and that's going to be like this is on the actual Tegra. This is the like memory layout for the applet, the NVT boot recovery applet. So you have your RCM message at the beginning, and it's just like all the various data, like the signature and like all this other stuff. You have the USB DMA buffers, which are basically you write whatever packet you want to send. There's 2 of them so that you can like be more efficient and not wait. And you can like do multiple different you can handle multiple different types of USB requests at the same time. So you basically write data into these DMA buffers, and then they will get written out for you over the wire as USB packets. And then you have the stack for the actual application that is doing all this stuff, the recovery mode application running as the boot ROM, essentially boot ROM level permissions. You have the status variable, which is like if you ask, and that's stored on the stack, and this will be important, but if you send a USB control packet that asks like what is the status of the USB device, the switch's USB device, this is where that's stored. And then you have your payload, which is in RAM right after the stack. So this is where the bulk endpoint will be writing like the payload. So yeah, so the bug because I don't want to spend too long on this, is basically that you have this 2-byte status that I showed in the memory layout that's on the stack, and you might issue a get status request over USB because you want to know the status of the device. And in a couple certain cases, basically it will use the length you specified in your USB request to reply with the status, copy out the status. So even though the status is 2 bytes, if we asked for, say, 16 bytes or 65,535 bytes of what the status was, well, what does it do? So it's going to copy onto the USB DMA buffer to write out the status about how much memory you asked for. And then the USB DMA buffer is theoretically going to be sending that data back over the wire. But what happens if we asked for, because the USB DMA buffer is not 65,535 bytes long. It's much, much smaller than that because you're not supposed to be sending USB packets that are that big. So it's going to copy all the memory after the status variable up, including large chunks of the RCM payload. And it's going to copy it right to that USB DMA buffer, overwriting the stack in the process. Yikes. So this can happen while our payload is still in memory before the signature is checked. So we're basically going to be sending this unauthenticated big payload of data that gets copied on top of the stack. And to make things even easier, the boot ROM does not have NX adept, whatever you want to call it, stack canaries, ASLR, any kind of modern mitigation, because it's running in this really, really low level environment that hasn't set any of that up yet. So if you've done any kind of exploitation in the past of basically any kind, you'll immediately recognize that a complete stack overwrite without any mitigations is just a GG. And this gives us CV 2018-6242. So this is just arbitrary code execution. You connect to the switch over USB. You use RCM to send over a payload that is basically what you want the stack to look like. You overwrite all the return addresses, whatever. The signature is invalid, so you need to not let the transfer of that payload finish. So it's like writing this data into the buffer. And as I said earlier, you can have different USB endpoints triggering at the same time. You can send different packets at the same time. So you're going to be sending a RCM command that sends this payload so that it's writing this payload into memory, but before it finishes writing, you send the get status command that copies all this data on top of the stack. So you just set a higher length in your request saying your payload's bigger than it really is, so it doesn't actually finalize. It copies all your data, and then it's expecting more data, so it's waiting, and you're just going to overwrite the whole stack with that still unauthenticated data, and overwrite all the return address pointers with whatever you want, hijack control flow, GG. This is actually a very simple exploit. So our impact, as I said, arbitrary code execution. You can now run whatever you want when you overwrite the return address. I believe you overwrite the return address of memcopy in particular here, but it's running as the boot ROM. It's just everything is compromised. So your root of trust is completely broken. No lockdown has occurred yet. So the boot ROM region itself is still unlocked. But also there's a bunch of key data like fuse regions that have all this very lucrative key material there. And it is, as we said about boot ROM bugs, completely unpatchable with a software update. So the later revisions of the switch, before the Switch Lite, later revisions of the original Switch started shipping with they call them eye patches. They're basically patches that can be applied at the factory. They set a fuse that prevents new patches from being applied after manufacturing is completed. So newer versions of the console had this bug fixed, but original versions will have this bug forever. Or so we thought. So we thought that this was GG and it was an unpatchable bug, but actually Nintendo had some more clever ideas up their sleeve. So now we're going to be talking about recovering a secure boot chain. And this is, honestly, I think this is really cool. This is one of the cooler things I've seen an embedded secure device do. So we have this exploit, and it goes public in like April 2018. I think it gets like leaked. Basically, like a ton of people had this exploit. Basically, everyone who glitched it saw it because it's just this very, very simple exploit. User-controlled memcopy on top of the stack. And the system is publicly broken for 6 months with no patch in sight. Everything's going great. And then version 6.2.0 releases, and almost everyone was completely unprepared for that. And Shocked Pikachu Face is a complete bombshell. Turns out the Switch had this other thing called the Tegra Security Coprocessor, and I talked about security coprocessors before, and it runs NVIDIA's proprietary Falcon ISA, instruction set architecture, and you can see Captain Falcon in the bottom right. We have a new foe. And basically the security coprocessor's job is to store a bunch of keys and decide when to give you those keys. And it's almost completely irrelevant to us before right now, and most people just forgot it existed, because when you boot the device up prior to 6.2.0, you basically needed 2 console unique keys to initialize your crypto system. And console unique means like every single device has its own key. It's not like one for every switch. And you need the secure boot key, which the boot ROM had, and you need the TSEC key for the Tegra Security Coprocessor, TSEC. You needed its key, and you would basically just ask it for the key, and then it would like put it in a register, and you just like decrypt or you'd like initialize the crypto system, and you could decrypt all your data. But you need this to decrypt like the OS, your applications, your games, like everything. And short of like a full re-implementation of the OS, you are basically stuck without like the ability to initialize this crypto system. And Nintendo realized this. So when the bug happened, they actually basically moved the root of trust in a very clever way. So they completely overhauled the crypto system and added this thing called the TSEC root key, which is a firmware specific, like shared across all consoles key that they would update with every single firmware. And the TSEC generates this key from like hardware secrets, or actually no, the key is contained. The key to decrypt the firmware containing this key is contained within hardware secrets. But basically, the TSEC firmware now contains this key and won't just give it to you. So you can't initialize the crypto system, you can't decrypt the OS, you can't continue booting. And the TSEC firmware is now signed and encrypted as opposed to just being signed, because that's an option that it has as a security coprocessor. So it can store these keys without you actually like seeing them. And you need this TSEC root key to boot versions of the OS Horizon above 7.0 or 6.2.0 and greater. You need this TSEC root key to do anything useful, basically, and only the TSEC can produce the key because it is stored in the firmware that you can't decrypt. Only the TSEC can decrypt it. So you basically, if you want to load the OS, you have to let the TSEC run its new firmware so you can get its key. And this is interesting because the new firmware did other stuff too. So it's a highly privileged security coprocessor. And what it's going to be doing is essentially it has the capability to hold the entire platform in reset almost, like basically everything. And holding in reset means like nothing is running on the system except it, and it checks to make sure this is the case. So what you're going to do as you boot the system up after the boot ROM on the boot and power management processor, the like actual bootloaders that Nintendo wrote are going to, and that you're going to now have to follow if you want the key, is going to basically upload the TSEC firmware into the TSEC if it like running the new updated version, and then it's going to suspend the whole platform. It's going to DMA like direct memory access, check all of your RAM, make sure that nothing has been tampered with at all, and that you actually like make sure that you're not messing with anything, that you haven't loaded unsigned like code, whatever. And then it'll write the TSEC root key to a write-only key slot. And that basically, the idea of a key slot is that, Actually, do I have a slide on this? Yes. Okay, and then it'll resume the system. And the idea of a key slot is that it's a hardware AES engine, where that means that there is a actual thing that'll do crypto for you on the system, and it can store keys, so you can like tell the crypto system, here is a key, and then you can ask it to decrypt and encrypt things for you with that key, but it won't actually let you read that key back out. So this lets you decrease privilege levels while still being able to decrypt data without exposing those keys to things with less privileges, which is very cool and useful, but not very great for us. So how do we run our homebrew on the new versions? Because we can't extract the hardware secrets out of the TSEC. We can't decrypt this firmware. We can't get the keys. We can't run code on the TSEC because it needs to be signed, so we can't just like write the key somewhere. What do? Re-breaking a secure boot chain. Actually, it wasn't that hard. So there's this thing called the SMMU, the System Management Unit, or System Memory Management Unit. It's basically the thing that's going to be mapping like pages of memory on your system, and most like computers have some kind of memory management unit, or probably several. And in this case, the TSEC sits behind the SMMU, and you can just configure it to map the memory that the TSEC will be checking to somewhere else, and say like, actually that address does not point to my bootloader, it points to over here in memory, and then just write like a fake bootloader there that is the real Nintendo one that isn't actually executing. So you give the TSEC like fake versions of everything, and then you pass the checks. And you know, TSEC sits behind this bus in the hardware, right? Like there's nothing you can do about that. And a couple people when this released, like I know, had already like realized this prior and to the new system update, just from looking at the security coprocessor out of curiosity. We're like, well, it'd be useless to ever use this security coprocessor because it's behind this thing that the application processor or the boot and power management processor controls, and therefore it's useless, right? So we now have this unpatchable thing that lets us just fool the TSEC to give us the key and say, here is my definitely legit bootloader. Or so we thought. So version 7.0.0 update comes out, and actually NVIDIA had a trick up their sleeve that they gave to Nintendo, which is a secret undocumented hardware register that lets TSEC just bypass the SMMU and read and write to RAM directly. And they also introduced a new TSEC root key since the 6.2.0 one was compromised. Well played, I guess. So that's a very handy trick for the security coprocessor to have, actually being able to read and write to all of the RAM without tampering. And yeah, so what do we do now? Well, the ending, I'm afraid to tell you, isn't that satisfying. So the TSEC signing key was basically acquired by private, unknown means by some individuals. We don't actually have... Nobody has this key except like two people. Nobody knows specifically how they got it, but they acquired the TSEC signing key, and then they made their own TSEC firmware, basically, that'll calculate all the keys for you, and then they signed a version of that open source firmware and released it. So now you can upload into the TSEC your own, well, quote unquote your own, this one validly signed open source firmware that will just calculate the keys and give them to you. But why not just release the signing key that they got? Well, two reasons that I can see. Maybe not their specific reasons, but my reasons that I would speculate. So number one is legal issues. So like you might recall the PS3 incident with GeoHot and their signing key, Sony's signing key for the PS3 being factored. That was like a huge thing. And you can see why one might not want to be involved in any kind of lawsuit over releasing copyrighted signing material, because that's just how intellectual property works in the US. And there's also this other problem that was going on around the same time, and this is kind of a clever hack, in my opinion, and I think this is really cool. It's a side tangent, because we're kind of at the end of our story here, but quick side tangent is that there's a couple commercial piracy groups that would release like basically they would take the open source exploits and they would kind of repackage them and throw their own name on them, and then they would sell them to people without making it clear that they were just selling a thing the person could get for free. And a lot of the open source people didn't like this. They felt like the closed source piracy groups were not interested in homebrew. Of course, they were interested in selling piracy, which homebrew people are not interested in, don't care about. But they were basically using all this effort that other people were doing to make an open platform for the Switch, and they were just selling this thing. So what they did was, with this new exploit, instead of releasing the signing key, which then the commercial piracy groups could use to just calculate the keys themselves and run their piracy software, they made a version of this, the firmware, that'll give you the keys, but before it gives you the keys, it actually initializes the screen and shows a splash screen saying that this is free and open source software, right? Instead of so that the user is forced to see this, and then it would give you the keys and continue the system boot. And the idea they had behind this was that now the commercial piracy groups would basically be forced not to use this exploit or this signed version of the firmware, because they didn't want to be seen their reputation couldn't handle being seen just obviously stealing this thing. And they were right. I think the piracy groups just didn't have a solution to run on the latest firmware versions for a very long time. I think they use side channel exploits to leak keys, or that is the consensus that I've heard, is that they basically managed to get the keys themselves eventually, but it took them a very long time. So reputation permanently damaged. So I guess success on that front. Yeah. So I don't actually know. Yeah. So here's our conclusion. I don't actually know when the next talk is. We will be sending out information on that with the same wherever you got it this time, you'll probably get it the same way. If you subscribe to our channel, you'll probably get a notification, hopefully, if YouTube works. But it'll maybe be next week. So yeah, stay safe, everyone. If you're an RPI student and have an RPI email, you can join our Slack and hang out. Cool. Yeah, hope everyone enjoyed and learned some cool stuff about embedded security and the Switch.